Okay, let's talk about separable equations and applications. So what is a separable equation, or specifically a separable differential equation? Okay, well, we've been talking about different order differential equations, specifically first order. We've seen some second order differential equations. So a first order differential equation, so let's just say dy dx. And we know that this could be a constant, right? We talked about the peanut butter problem, right? The price versus the month. I did a rodent problem in a previous example. And sometimes our differential equations are very simple. We have a nice constant here, or sometimes we have a nice function of x, right, of the independent variable. Uh, but sometimes we have more than one variable, right? It's a multivariable function. So what if our differential equation can be expressed as a function of x and y, or u and t? I mean, it could be any variables depending what physical quantity you're talking about. Okay, so let's go ahead and write this down. So we say, so this obviously is this first order, right, because the highest derivative is 1. This first order differential equation is called separable, provided that our h of xy, right, that this function, if it's separable if we can rewrite our h of xy as a product of functions of x and of y, or if you're talking about u of t, then a function of u and a function of t. So let's go ahead and write that down. So we say let's maybe use a different color here. I don't know, we'll do pink. Okay, so we say it's separable. So if and only if, IFF, it's just a nice shortcut we us mathematicians like to use. So it is separable if and only if we can rewrite, so I'm talking about my h of xy here. If I can rewrite that as a product of, so product multiplication of the function of x, so I'll just call it g of x, and maybe little h of y. Okay, so we have this. Now remember, h of x and y is the same thing as dy dx as stated from above. And I can rewrite, okay, so g of x is a g of x. I want to write h of y, so let's just say here h of y is going to be 1 over f of y, right? I'm allowed to rewrite that function, so I can rewrite it like this. And the reason I want to do that, so dy dx equals, I can say g of x over f of y. So technically we have a difference of two functions, but we really have a product here, because division is really just the reciprocal of multiplication. So okay, so moving on, so let's simplify this a bit. If we use a little bit of algebra, right, this is a proportion, so I can definitely cross multiply, or you can multiply by the LCM, which is dx f of y, if you want to think about it like that. That's really where cross multiplication comes from. So if I cross multiply, I get, okay, dy times f of y equals dx times g of x, and I'm going to write f of y first, times dy equals the functions first, g of x times dx. So here in this case, the variables, right, my variable y and my variable x, right, or function of y, function of x, I separated the variables here, meaning I isolated the variables on opposite sides of the equation. So when you can do this, we say it's a separable equation. You'll notice in section 1.1 you solved differential equations you found the either general or particular solution, but all you did was integrate. You notice the left-hand side of the equations, right? They were all nice dy dx's, and it was really just technique of integration. But what happens when you can't do that all the time, when you can't just integrate one time and simplify? Well, this is where you have another, tool in your box. You want to ask yourself, can I separate these equations? So again, that's the reason why we're moving on to 1-4. And here, so we want to know what our unknown function is. And then here, I think for integral, I forgot what I used. If it was pink, it really doesn't matter. So if I integrate both sides, I want to, so integral, the next step. And I'm going to write f of y dy. And then I can integrate g of x, right, dx, and then I usually add a constant integration when I integrate. And I mean, then again, this is just techniques of integration after you separate your variables, where you're integrating with respect to y, and then here this integral is just with respect to x. But we know that this is just going to be, again, it's going to be integrals. And so another way of saying that is antiderivatives. So we can call this f of y. Your book calls it f of y. We have our little g here, so this is going to be called our g of x, right? If you had capital T or little t of x, it would be capital T of x. So this is again the big picture for separable equations, and I'll go ahead and do some examples in the next few videos. And one thing I'll say is when I find the particular solutions, that is when I'm given a specific initial condition, some of the functions are very nice, right? They're lines or maybe quadratic equations, exponential functions, but some are a little bit funkier, so I won't graph those, but I mean, you can use your calculator, your graphing calculator, that's fine. But remember that a particular solution, right, is one solution out of infinitely many other solutions of a differential equation, right, given that a specific or that initial condition. Okay, I'll see you in the next video.